Okay, let's see how to figure out calculate the area between two curves. So what we've done in the past so far is we know how to integrate, which gives us the area underneath the curve in the x-axis. So if we consider that, let's just think about this for a second. Let's just say we've got some curve. And we want to know, if we want to integrate, let's just say, from a to b of this function, f. This is from a to b, f of x, dx. We came up with this integral from looking at rectangular sections, right? So we would split this up into little sections, and if we took enough of them, we got a very good estimate, and if we took more than enough and we took an infinite amount, we got the exact area. So if I pull out one of these rectangles here, just some rectangle here, right? Remember we call this maybe, these are our delta x. This is the width of our rectangle right here, delta x, right? And the height of our rectangle was f of x. And so if we took it at any random, we could take it at any random place on our rectangle if we took enough rectangles, right? If we took enough, it didn't matter if you took it from the left end point or the right end point or the mid end point. If you take enough of them, an infinite amount, you can pull it from anywhere in that subinterval. So we call it f sub I. X sub I is the place we might pull it from. This might be, say, okay, this is x sub I, somewhere on this interval. The height would be f of x sub I, and the width is delta x. So the area of this rectangle would be the width, delta x, times the height, f of x sub I, and we would sum up all of our rectangles, right? And so the width, delta x in general, is equal to b minus a over the number of rectangles that we took, number of subintervals that we took. Okay, this is what we would do. So if you think about that, this is already a subtraction of two functions. We're about to see that we're going to be subtracting two functions. If we want the area under the curve, what we didn't write here was that we're taking the height is f of x minus the height of this curve. Well, this curve is the x-axis, and this curve is also known as y equals to 0 or f of x equals to 0. So we took this function minus this function, 0. This is what we don't ever write. We don't, minus 0 is just the same thing, so we don't write that. But you can even think of it as this function minus this function. All right, so what happens if we want to calculate the area between two curves? And we'll call this guy f, and we'll call this guy g. If it turns out that this function is always above this function for the integral we're interested in from a to b, let's say this is a and this is b, right? Then we can simply take the height of our rectangular section. Let's just pull one out, right? The height of our rectangular section right here is going to be f of x sub I, this height, minus g of x sub I, minus this guy's height. From here to here, that's going to be the height. And so we will just take this times the width, and that's going to give us the area of the rectangle, and then we're just going to sum up an infinite amount of these. Okay? That's how we're going to get this, which ends up being an integral. So to calculate the area between any two curves, we can take upper function minus lower function times the width. And that will give us a bunch of rectangles to add up and calculate the area. So let's see how this works. What if you've got I've got the box on your worksheet right there. It says the area. The area A of the region bounded by the curves y is f of x and y is g of x, and the lines x is a and x is b, where f and g are continuous, and where f is greater than or equal to g of x for between a and b, is equal to this integral. The area between these curves is equal to the integral from a to b of minus g of x dx, just like that. All right, let's try it out. There's a picture for number 1, which is a nice picture. It says, I'll try to just copy the picture a little bit. Find the area of the shaded region. All right, so let me catch up with you guys. Here's number 1. We've got some curve here that kind of goes like this, and then we've got another one that kind of goes like this, sort of looks like that, and they said it kind of goes more like that. Okay. Find the area of the shaded region. So let me make sure we agree with our shaded region. It's this part in here, right? To this point. Okay. It's this region right here that we're after. Okay. So they named our function, the upper function, the highest one is y is e to the x. So this guy right here, this is e to the x. And then the lower function is x e to the x squared, okay? That's the lower function. And then there's a point where this is the end point, this is the origin right here, right? And then this is the point here called 1e. 1e. All right, so if we look at this, we've got these two curves. We've got an upper curve and a lower curve. So what is our a and b? What is our integral of integration? Well, this x value right here of the shaded region is x is 0. That's our lower limit. This x value right here, where our region stops, this x value is 1. We're going to integrate from 0 to 1. Of what? Of upper function minus lower function. Our upper function is e to the x. Our lower function is x e to the x squared dx with respect to x. All right, let's see what we can do here. We need to integrate this. I'll probably split my integral into 2 separate integrals. So this is the integral from 0 to 1 of e to the x dx minus the integral from 0 to 1 of x e to the x squared dx. Okay, this integral is just e to the x. 0 to 1. Okay. This one is going to be u substitution. So I'm going to let u be x squared. Du is going to be 2x dx. So 1/2 du is x dx. So if I want to rewrite this in terms of u, if I say 1/2 du, maybe I'll change colors because I'm getting this off. Let me make this look to the side. Right here, I said let's let u be x squared. Let's let du be 2x dx. So 1/2 du is x dx. So if I rewrite this guy in terms of u, to get the x dx, how did I get that? If I write down 1/2 du, I get that. And then I need e raised to the x squared or e raised to the u. I can either remember I've got limits there and then change it back to 0 and 1 when I put it back in x's, or I can rewrite it in terms of u. I guess I'll rewrite it in terms of u. Right here, 0. If I let 0 go in for x, 0 squared is 0, so it'd be 0. If I let 1 go in for x, 1 squared is 1, so this upper limit would still be 1. That is unusual that the limits would stay the same, but sometimes they do. All right, that's fine. Let's evaluate this. This is minus 1/2. Integral of e to the u is still e to the u from 0 to 1. This is e to the x from 0 to 1. So, this is e to the 1 minus e to the 0 minus 1/2 e to the 1. And this is going to be a plus because this would be e to the 1 minus e to the 0, but this distributes, so it's going to be plus 1/2 e to the 0. So what do I get here? I get e to the 1, e to the 1, minus e to the 0, minus the number 1, minus 1/2 e, minus 1/2 e, plus 1/2 e to the 0 plus 1/2 times 1. All right, let's see. This is 1e minus 1/2 e. These are like terms that can be combined. This is really 1/2 e. This is a negative 1 plus a 1/2 minus 1/2. This is what this equals to, 1/2 e minus 1/2. All right, that is example 1. How about 2? We've got a different looking curve there. How would we handle that? The second curve we have here, set of curves I should say, that we have to find the area to, it looks like this. We have something kind of like that. I got to be a little more careful where I put my axis. And then we have something that's kind of like this. Okay. I'm going to have to cheat a little bit and draw my axis where I need it to be. This is where I need my axis to be, right here and right here. All right, let me see if I can clean this up a little bit. Okay, so we kind of have a picture that looks like this. All right, it looks a little sloppy, but you have it on your paper. So, all right, right here, they said find the area of the shaded region. So this is the shaded region we're trying to find this time. Okay, I'm going to approach this one a little bit differently simply because of the way the curves ended up being. So let me just see here. This, where did my X go? So I have a curve like this and I have a curve like this. And so part of the time, it's not clear who is always above the other. That's not clear. Over here it was really clear. E to the X was always higher than this one. That was clear. Over here, it's not as clear. So what I'm going to handle this one, you can also kind of orient it the other way. And you say, okay, well, let's calculate it from right to left. If we look at this curve right here, what is his name? It is called, well, I'm just going to call it X on the right. And this curve right here is X on the left. This one is always to the right of that one. And so I can say, okay, let's orient it with respect to Y and then take the right side minus the left side. And we can do that. So at this point, instead of looking at the X values, we're integrating with respect to Y. So we're going to say, what are the Y, how far down do we go and how far up do we do? So right here, this Y value is 0, right? And where do they intersect? They intersect up here at -3, 3. So we're doing it with respect to Y. So our limits of integration are going to be from 0 to 3, and this is going to be with respect to Y. Now I'm going to look at the curves, and the curves that they gave me, nicely they wrote them in terms of Y. So X, what I call X sub R, or the right side, is equal to 2Y minus Y squared. And X sub L, the left side, is equal to Y squared minus 4Y. Is that right? Yes, it is. Okay, so now you can set up your integral. Instead of going high to low, you can also go right to left, if that's easier, and it's easier in this case. So what you have to do is write X in terms of Y. So let's see, we're going to take X to the right, 2Y minus Y squared, this curve, minus X left, Y squared minus 4Y with respect to Y, and we'll integrate it this way. All right, so this becomes 0 to 3, 2Y minus Y squared. Let's distribute these negatives and collect like terms. Minus Y squared plus 4Y. So we get negative Y squared minus Y squared gives me -3Y squared. 4Y plus 2Y gives me a plus 6Y. And this is with respect to Y. If we integrate, this becomes -3Y cubed over 3 plus 6Y squared over 2 from 0 to 3. Okay. 3 divided by 3 is a 1. So we basically have negative y cubed. 6 divided by 2 is a 3. All right, so let's plug this in. We have a negative 3 cubed is 27 plus 3 times 3 squared is a 9 minus 0. All right, we got, something went wrong there. Let me see what I did wrong here. Hang on. Negative 2y squared is what I got here. Yeah, okay, I'm totally agree with that. I see my mistake. Negative 1 minus 1 is 2. Better. All right, so what's that going to do? It's going to say y cubed over 2. All right, let me fix my mistake. Plus 3y squared. Okay, this becomes, all right, let me fix it here. This integrating goes y cubed over 3 times negative 2. All right, this is what I have. So I have negative, so basically negative 2/3 times y cubed. That's going to be better. All right, so negative 2/3 times 3 to the third is 27 plus 3 times 3 squared is 9 minus, when we put in zeros, we get a big old 0. All right, what are we going to get here? 3 goes into 27 9 times. Negative 2 times 9 is negative 18. 3 times 9 is 27, and when I add those, I get a 9. And so that is what this area is 9. Is how we can figure that out. All right, now let's do some, we don't get a picture, but we just have to, maybe sketch them and figure it out. Let me see. Okay, I'm going to stop this to give you a little break, and then we'll look at the last few examples.